biomedical image processing course. In this module, we will try to cover the two-dimensional CWT wavelet used for feature extraction. The main 2D CWT concepts and properties used in this module are presented in the following slides. The real plane R by R is denoted as R square and 2D vectors are represented as the bold letters, example x, b, k, epsilon, r square. Images are taken as finite energy function, that is square integral f epsilon r square of L square of r square. The vector x is used to represent a spatial position in the image, while k is associated to the given spatial frequency. The spatial frequency domain is defined by the two-dimensional Fourier transform f dash of a given image f as f dash of k equal to 2 pi inverse integral exponent minus ikx into f of x d square x. Using that, the 2D Fourier transform can use to extract the region of interest. And analyzing wavelet psi epsilon L square r square may take on complex values and must satisfy the admissibility condition described in successive slide. A family of wavelet, that is psi ba theta of same shape, is defined by translation, dilation and rotation by b, a and theta respectively of the analyzing wavelet. So psi ba theta of x equal to a inverse psi in bracket a inverse r minus theta of x minus b, or psi dash ba theta of k equal to a exponent minus k bk psi dash of ar minus theta of k, where a greater than 0 and r theta denotes the usual two-dimensional rotation. R theta of x equal to x cos theta minus y sin theta, comma x sin theta plus y cos theta, comma theta is in between 0 and 2 pi. The translation, dilation and rotation operations generate the two-dimensional Euclidean group with dilations acting over L square of r square, which is denoted by g. The CWT T psi epsilon L square of g are defined as the scalar product between f and each wavelet psi ba theta as a function of ba theta epsilon g, which is equal to T psi of ba theta equal to psi ba theta over f equal to a inverse integral psi star a inverse r minus theta of x minus b into f of x d square x, or it can be written as a integral exponent I bk into psi dash star of ar minus theta of k into f dash of k d square k. Using that, the scalar product is possible to determine. The transform is thus a local representation in each of the four dimensions of G, capable of revealing dilation and rotation symmetries. The psi and psi dash are well localized. The transform act at constant relative bandwidth, that is, the bandwidth of the filter is always proportional to the analyzing frequencies. Thus, as in the 1D case, the transform presents high frequency precision in low frequencies and high spatial precision in high frequencies. This explains why the wavelet transform is suitable for detecting image singularities such as edges in the images. The wavelet transform conserves energy and provide a linear decomposition of f in terms of the wavelet family, that is psi ba theta with coefficients t psi of ba theta. The transform can be inverted, providing a reconstruction of the original signal from the coefficients as f of x equal to c psi inverse integral t of ba theta psi ba theta of x into a to the power minus 3 d square b d a d theta, where c psi is the normalized constant. For the above formula to hold, the wavelet admissibility condition must be met by the equation shown on this slide. It has c psi equal to 2 pi square integral mod of psi of k square into mod k to the power minus 2 d square k is less than infinity. If psi satisfy psi epsilon L square r square, psi epsilon L to the power 1 r square intersect L square r square, then the admissibility condition reduced to requiring that the analyzing wavelet has zero mean. Psi of 0 equal to 0 to integral psi of x d square x equal to 0. Besides the admissibility condition, additional desirable properties may be defined, such as the psi and psi dash be well localized and that y represent a certain number of vanishing moment, thus being blind to polynomials up to the corresponding degree. The CWT can be implemented efficiently employing the fast Fourier transform, that is FFT, and its Fourier domain definition can also possible to implement on the retinal images. Otherwise, for analyzing only small scale, the analyzing wavelet may be cropped off in the spatial domain so that the standard correlation implementation might actually become faster. The CWT information is highly redundant and in practice it is generally calculated over a discrete family of wavelet, that is psi bi ai theta I. An approximate reconstruction formula can then be given by f approximate of x equal to summation of psi bi aj theta k t psi in bracket bi aj theta k, where I j k varying with certain limit. In this case, f dash is the reconstruction version of f. The parameters bi aj theta k should be chosen to provide a stable reconstruction. Definition: the so-called frame. The precision of the analyzing wavelet is studied in order to provide directives for defining a suitable sampling so that the frames may satisfactorily cover the spatial and frequency domain. Even so, the resulting representation will necessarily be redundant in contrast to the DWT, which allows for deriving orthogonal bases. Now we will see two-dimensional Gabor wavelet, how it is useful for extracting prominent lesions. The 2D Gabor wavelet has been extensively used within the computer vision community with special attention to its relevance to studies of the human visual system. One of its most important properties is its capability of detecting and analyzing directional structures. It is also optimal in the sense of minimizing the inherent uncertainty in the spatial and frequency domains. The 2D version of the Gabor filter was probably introduced in which together with show that the filter represents a good model for simple cell of visual cortex. In a subsequent slide and the research work done by the researcher, Dogman suggested the generalization of the filter to a wavelet which was then called Gabor wavelet. On the other hand, Antoine Murenji and collaborators introduced the generalization of the CWT to two or more dimensions based on coherent state and group theory, in which the same wavelet was called Morlet wavelet, being the natural generalization of the 1D Morlet wavelet. The 2D Gabor wavelet has certain other properties which are also useful for extracting the prominent lesions. The name most common adopted in the computer vision community is Gabor wavelet, which is therefore also used in this particular work. Application of the 2D Gabor wavelet in computer vision include object representation, particularly face images, texture detection and segmentation, and oriented structure analysis. The 2D Gabor wavelet has also been shown to outperform other linear filters for detecting of oriented features, and if we used oriented features we can able to get their direction so that thickness, length, etc. can be possible to calculate. The 2D Gabor wavelet is defined as psi g of x equal to exponent ik0x exponent minus 1 by 2 xax plus corrections. Psi dash g of k equal to det b raised to 1 by 2 exponent minus 1 by 2 k minus k0 into b of k minus k0 plus the correction factor, where A is 2 by 2 positive definite matrix that defines the wavelet anisotropy, B equal to A inverse, and K0 epsilon r square defines the complex exponential basic frequency. The anisotropy matrix is taken as A equal to psi inverse 0, 0, 1 with 2 by 2 size, with elongation given by epsilon greater than or equal to 1. The wavelet smooths the signal in all directions but detects sharp transitions in the direction of K0. In spatial frequencies, Gabor wavelet is given by a Gaussian function center at K0 and elongated by epsilon in the ky direction. It is thus well localized both in position space around the origin and the spatial frequency space around K0 factor. Angular selectivity increases with mod of K0 and epsilon. These effects can be combined choosing K0 equal to 0, ky and epsilon greater than 1. Figure 8.1 shows the effect of changing the wavelet's parameter both in space and spatial frequencies. This figure shows the effect when we change the wavelet, how it affects on getting the space and orientation. The effects changing the wavelet parameters both in space as well as spatial frequencies. The correction term is necessary to enforce the admissibility condition psi dash g of 0 equal to 0. However, it is worth noting that the term is numerically negligible for mod k0 greater than or equal to 5.6 and in many situations can be simply dropped out. We do not use the correction term since it implies a loss in spatial location, that is mod psi g square becomes bimodal, and this problem should be addressed in future successive studies. The definition of a directional wavelet is stated in terms of its spatial frequency domain support. An analyzing wavelet is said to be directional if its effective support in the spatial frequency domain is contained within a convex cone with apex at the origin. Wavelets with directional support only in the spatial domain may not be able to detect directional structure, as is the case with the anisotropic Mexican hat, which does not satisfy the previously given definition. This is one of the limitations of 2D DFT while using Gabor wavelet on the image domain. The Gabor wavelet is thus said to be directional as its spatial frequency domain supports in an ellipse given by the elongated Gaussian, as can be seen in the example of figure 8.1 which was shown in earlier slide. If the definition is to be strictly observed, the Gabor wavelet is only approximately directional given the Gaussian trail that are outside the ellipse but are numerically negligible. The resolving power of the Gabor wavelet has been analyzed in terms of its scale and angular selectivity, helping define wavelet frames that tile the spatial frequency domain. Many other 2D analyzing wavelets have been proposed in the literature, designed for specific problems, and the reader is referred to for a review work which has been done by the other researcher in their own domain. In the case of vessel segmentation, the Gabor wavelet should be tuned to a suitable frequency so that vessels may be emphasized while noise and other undesirable structure are filtered out. For the methods presented in this module, the parameters were set to epsilon equal to 4, resulting in an elongated wavelet, and k0 equal to 0,3, providing a low frequency complex exponential with transition in the direction of its smaller axis as shown on the bottom row of the figure 8.1 which has come across in earlier slide. The Gabor wavelet's capability of detecting oriented features is fundamental in blood vessel detection. It is interesting to note that the wavelet shape is locally similar to that of blood vessel and is preserved across different orientation as well as scale. Therefore, stronger wavelet responses are produced when the wavelet is found at the same position, orientation and scale as a vessel in the image. Now let us summarize this module. We have started this with 2D CWT, then we come across with 2D Gabor wavelet, its use and how it is possible to use for the feature extraction of retinal images because it has very high properties. In successive module, we will try to cover supervised classification, Bayesian decision theory, Bayesian Gaussian mixture model classifier, etc. We have certain prominent references which one can see to go for detail and which may be helpful to expand your work. Thank you very much.